Hey everyone. Recently I've been thinking about making this game using Python, but to create that game I need this thing called Perlin noise, which is a pseudo-random pattern with some sort of smoothness to it to make it look more natural. A video from the coding train demonstrates the usage of Perlin noise in a language called processing. I initially thought that there'd be an easy way to implement Perlin noise in Python, but surprisingly there wasn't. I mean, Python is known for having a wide range of applications, and you'd expect that something as simple as Perlin noise would be available as a Python module. Now I did find this project on pypy.org which said to do pip install noise, but there were two problems with this. One was that I just got a flat out error when I ran the command, and I probably could have gotten a solution on Stack Overflow, but I didn't even bother because of problem number two, which was that the site did not have links to any documentation. I did some more searching, but I couldn't find anything particularly helpful. So after some frustration, I decided that the best way forward was to just create my own Perlin noise generator. So I did just that. All the code is on GitHub and I'll link to it in the description. You can download it and use it for your own project or even throw it into your site's packages folder. For the rest of the video, I'm just going to explain exactly how the noise algorithm works and how you can use my code. In a simple random noise generator, a random value is assigned to every point on a number line independently without relation to any of the surrounding values. But if you want to smooth out the random pattern, a good idea would be to introduce random values at intervals. The points in between will be influenced by the surrounding values depending on their position. To see how these intermediate values are assigned, let's just focus on one interval. Suppose this interval contains point t, and there are random values at the interval boundaries which we'll call a1 and a2. Therefore, the value associated with the point can be based on a weighted average of a1 and a2. This is known as linear interpolation because the result of doing this at every point is a straight line. And this seems okay, but if you look at the next interval, you get a corner or a cusp in between. To resolve this, we need to ensure that the derivative of the curve approaches the same value from both sides. Now we might represent the simple interpolation amount as a ratio between how far right the point is within the interval and the size of the interval. Then, we can modify this value by running it through an ease function like this one. Not only does this yield a number close to the input, but it also has the special property of having a slope of 0 at x equals 0 and x equals 1. This means that the slope of our noise curve will equal 0 in between intervals, so the final result is continuous and differentiable at every point. And that's all there is to it. Let's take a quick look at the code. Here I created a class called Perlin, and an instantiation of this class will allow you to extract random values. Each object has a gradients list, which is just a list of random values that are assigned at specific intervals. A frequency has to be specified in the constructor argument in order to indicate how frequently a random value is assigned. In this case, it indicates how many values are assigned from 0 to 100. This probably is not the standard definition of frequency in Perlin noise, but I could not find any good explanation for it online. If anyone understands the proper implementation, please do share it in the comment section, but for now, I think this should suffice. Down below, I created a value@at method, which takes in parameter t and outputs the corresponding value. The bulk of the algorithm is done here, and there are a few auxiliary methods, such as the ease method and the lerp method, which is doing the linear interpolation. You'll also notice this discard method here. Sometimes when you're producing a stream of values, you don't care about the previous values, so discard will delete unnecessary elements from the gradients list and change the lower bound. This is mainly to save memory, but in reality, running out of memory is unlikely unless you run this for a very long time. But it's nice to have this tool available if you need it, and I think it's good practice to use it when appropriate. So that's basically it for the Perlin class. Let me show you how to actually use this for a script. Here, I created two methods to demonstrate the difference between Perlin noise and purely random noise. To generate Perlin noise, I created a Perlin object called noise and used a value@at method at each integer from 0 to 199 to obtain a series of values, which I then graphed using matplotlib. For random noise, I'm just graphing completely random numbers at each point. If I call show Perlin noise, I get this smooth curve that randomly fluctuates over time. On the other hand, if I call show random noise, I get this messy looking pattern which looks completely unnatural because of the fact that there is no relationship between the points that are close together. So you can see why in games, Perlin noise would be more preferable, especially when you're trying to create natural looking designs. So hopefully this is helpful for any of you who need to use Perlin noise in your Python program. If anyone happens to know an already existing Python module that generates Perlin noise, please post a link to it in the description because chances are that that module is better developed. My code is still pretty crude, but it's doing what I hoped it would, and I think many could find this useful. I worked on this for weeks, and I'm pretty sure that there should be no issues, but if any of you find a bug, please bring it to my attention by posting a comment or making a pull request on GitHub. Over time, I hope I can perfect this and make this more robust. But that's it for this video. As always, if you have any questions, please feel free to ask them in the comment section. If you enjoyed this video, please consider liking and subscribing, and I'll see you next time.